Dear students, in this chapter electromagnetic induction and AC alternating current, we are going to study about the phenomenon of electromagnetic induction. And in this first video, let us have an introduction about electromagnetic induction, then the magnetic flux linked with a coil, in Faraday's experiments on electromagnetic induction, Faraday's laws of electromagnetic induction. Now let us study about the chapter electromagnetic induction and alternating current. As Michael Faraday said, nature is our kindest friend and best critic in experimental science if we only allow her intimations to fall unbiased on our minds. So by studying this unit, you are going to know about the phenomenon of electromagnetic induction, the application of Lenz's law to find the direction of induced EMF, the concept of eddy current and its uses, the phenomenon of self-induction and mutual induction, the various methods of producing induced EMF, the construction and working of AC generators, the principle of transformers and its role in long-distance power communication, the notion of root mean square value of alternating current, the idea of phasors and phase relationships in different AC circuits, the insight about power in an AC circuit and waterless current, the understanding of energy conservation during LC oscillations. Now, let us see what is electromagnetic induction. In the previous chapter, we have learned that whenever an electric current flows through a conductor, it produces a magnetic field around it, and this was discovered by Christian Oyster. Later, Ampere proved that a current-carrying loop behaves like a bar magnet. These are the magnetic effects produced by the electric current. Then the physicists began to think of a converse effect. Can we produce an electric current with the help of a magnetic field? A series of experiments were conducted to establish the converse effect. These experiments were done by Michael Faraday and Joseph Henry, almost simultaneously and independently. These attempts became successful and led to the discovery of the phenomenon which is called as electromagnetic induction. Michael Faraday is credited with the discovery of electromagnetic induction in 1831. So in this chapter, we are going to see a few experiments of Faraday, the results and the phenomenon of electromagnetic induction. And before that, let us recollect the concept of magnetic flux linked with the surface area. So this is the surface area, and the magnetic flux linked with that area is given by B. Now let us see what is magnetic flux. It is denoted by the letter phi B, and the magnetic flux phi B through an area in a magnetic field is defined as the number of magnetic field lines passing through that area normally, and is given by this equation phi B equal to integral B dot dA. Now this integral is taken over the area A, and theta is the angle between the direction of the magnetic field and the outward normal to the area. So we have this equation. If the magnetic field is uniform over the area A and is perpendicular to the area, then we will get this equation phi B equal to integral phi dot dA, that's equal to BA cos theta, and if theta equal to 0, then cos 0 is 1, so we can write this phi B as B into A. What's the SI unit of magnetic flux? That is given by Tesla meter square, as Tesla is the unit for magnetic flux and magnetic field V, and A is the area, so meter square. It is also measured in Weber, that is denoted by the letter WB. So when 1 Weber is given by 1 Tesla meter square. Then we are going to study about this Faraday's experiments on electromagnetic induction. The first experiment is this. For that, let us consider a closed circuit consisting of a coil C of insulated wire and a galvanometer G as shown in this figure. The galvanometer does not indicate the deflection as there is no electric current in the circuit, and a bar magnet is inserted into the stationary coil with its north pole facing the coil. There is a momentary deflection in the galvanometer, and this indicates that an electric current is set up in the coil. And if the magnet is kept stationary inside this coil, then the galvanometer does not indicate deflection. and the bar magnet is now withdrawn from the coil. The galvanometer again gives a momentary deflection, but it is in the opposite direction. That means the electric current flows in the opposite direction. And if the magnet is moved faster, it gives a larger deflection due to a greater current in the circuit. And if the bar magnet is reversed, the south pole now faces the coil. When the above experiment is repeated, the reflections are opposite to that obtained in the case of a north pole. And whenever there is a relative motion between the coil and the magnet, there is so by this experiment, we see that if the magnet is kept stationary and the coil is moved towards or away from the coil, similar results are obtained. And it is concluded from the experiment that whenever there is a relative motion between the coil and the magnet, there is a deflection in the galvanometer, indicating that the electric current is set up in the coil. Now we will see about the second experiment. For this, let us consider two closed circuits as shown in this figure 4.3a. That's here. There is a coil which is connected to a battery through a key, and here there is a galvanometer which is connected to this coil, which shows a right hand side deflection. Here the circuit consisting of a coil P, a battery B, and a key K is called as the primary circuit, whereas the circuit with a coil S, the galvanometer G, is known as the secondary circuit. The coils P and S are kept at rest in close proximity with respect to one another, and if the primary circuit is closed, the electric current starts flowing in the primary circuit. At that time, the galvanometer gives a momentary deflection as shown in the figure, and after that, the electric current reaches a certain steady value, there is no deflection in the galvanometer. Likewise, if the primary circuit is broken, the electric current starts decreasing, and there is again a sudden deflection, but it is in the opposite direction as shown in this figure. So here, as the current increases, the deflection also increases. That's on the right hand side. Whereas here, if the current is decreased, there is a deflection on the left hand side, deflection in the galvanometer. And when the electric current becomes zero, the galvanometer shows no deflection. So from the above observations, it is concluded that whenever the electric current in the primary circuit changes, the galvanometer will always show a deflection. Now let us see what is Faraday's law of electromagnetic induction. So it is realized by Faraday that whenever the magnetic flux linked with the closed coil changes, an EMF, that's an electromotive force, is induced, and hence an electric current flows in the circuit. And this current is called as induced current. The EMF giving rise to such current is called as an induced EMF. This phenomenon is known as electromagnetic induction. So here you can see this diagram which shows right hand side deflection in the galvanometer as the coil is connected to the galvanometer and the magnetic flux link is less. That's the magnetic flux link with this coil due to the presence of a magnet. And here, if the magnetic flux link is more, as you are bringing this magnet closer to the coil, it shows more deflection on the right hand side. Whereas here in this case, if the magnet is close to the coil, there is more deflection, and when you are moving away from this coil, the flux link to the coil changes and decreases, therefore the current also decreases. So based on this idea, Faraday's experiments are understood in the following way. In the first experiment, when a bar magnet is placed close to a coil, some of the magnetic field lines of the bar magnet pass through the coil, therefore the magnetic flux is linked with the coil. And when the bar magnet and the coil approach each other, the magnetic flux linked with the coil increases. So this increase in magnetic flux induces an EMF, and hence a transient electric current flows in the circuit in one direction, as shown in the figure 4.4a. Here, there is a deflection in the galvanometer. And at the same time, when they recede away from one another, the magnetic flux linked with the coil decreases. The decrease in magnetic flux again induces an EMF in the opposite direction, and hence an electric current flows in the opposite direction, as shown in this diagram 4.4b here. So there is a current in the opposite direction as shown by the deflection in the galvanometer. So there is a deflection in the galvanometer when there is a relative motion between the coil and the magnet. And in the second experiment, when the primary coil P carries an electric current, a magnetic field is established around it. And the magnetic field lines of this field pass through itself on the neighboring secondary coil S. When the primary circuit is open, no electric current flows in it, and hence the magnetic flux linked with the secondary coil is 0, as shown in 4.5a. Here, there is no current in the secondary coil. And however, when the primary circuit is closed, the increase in current builds up a magnetic field around the primary coil. Therefore, the magnetic flux linked with the secondary coil increases. And this increasing flux link induces a transient electric current in the secondary coil, as shown in 4.5b here. So there is a deflection in the galvanometer. And when the electric current in the primary coil reaches a steady value, the magnetic flux linked with the secondary coil does not change, and the electric current in the secondary coil will disappear. Similarly, when the primary circuit is broken, the decreasing primary current induces an electric current in the secondary coil, but it is in the opposite direction, as shown in 4.5c. Yeah. There is a deflection in the opposite direction, as shown in the galvanometer. So there is a deflection in the galvanometer when there is a change in the primary current. And these conclusions of Faraday's experiments are stated as below as two laws. The first law states that whenever a magnetic flux linked with a coil closed circuit changes, an EMF is induced in the circuit, which lasts in the circuit as long as the magnetic flux is changing. The second law is the magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. So this is the second law. If the magnetic flux linked with each turn of the coil changes by d phi b in a time dt, then the induced EMF in each turn is given by this expression. E is given by d phi by dt. If a coil consisting of n turns is tightly wound such that each turn covers the same area, then the flux through each turn will be the same. So the total EMF induced in the coil is given by this expression, E equal to n d phi b by dt, or d times n phi b by dt. Here n phi b is called the flux linkage, defined as the product of number of turns n of the coil and the magnetic flux linking each turn of the coil phi b.
I am Michael Faraday. Let us say about the laws of electromagnetic induction. First law. Whenever magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit, which lasts in the circuit as long as the magnetic flux is changing. Second law. The magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit.